Hello scientific people, how are you today? Today we are going to discuss about a very important topic, that is law of flotation, center of buoyancy and the basic concept of flotation. So before you actually view this lecture, what am I suggesting is you just see the video of Archimedes principle which I had uploaded in my channel. So that that is because the law of flotation is actually an extension of the Archimedes principle, and what is buoyancy, what is buoyant force, that I have discussed over there, right? So let's move on with the basic concepts over here. Here is a measuring cylinder that is shown in front of you, and this measuring cylinder is initially filled with some amount of water. So this water which is filled till here, let's call this as V1 ml, and we know that 1 ml is 1 centimeter cube. So I can also write down V1 centimeter cube, and that is equal, you can see that it is equal to 20, right? So it is filled till here, so it is 20 centimeter cube, correct? Okay, now we are immersing a stone in it completely, and when I immerse this stone completely, the water level rises. So earlier water level was here, now afterwards the water level rises till here. So this is the rise in the water level, and we can see that the final level is 23 centimeter cube. So the final volume in centimeter cube, that is equal to 23 ml or 23 centimeter cube, right? So I may find out the difference in the volume, that is the amount of water that has gone up. So that is 23 minus 20, so that is 3 centimeter cube. I can also write down this as 3 ml, right? So what is 3 ml or 3 centimeter cube? So it is this part of the water that I am showing you. So what is this green color part that I am showing you? That is the volume of liquid displaced, and that is same as the volume of the irregular object. So volume of liquid displaced is equal to volume of the stone immersed, correct? So this is a very basic thing that we have been learning, but this concept is to be remembered over here, right? So what happens is, if I immerse half of the stone, then also the water level will go up. Then the difference in the water level would be this is V2. The difference in the water level would be equal to half the volume of the stone, correct? Okay, so let's move on. Here what I have shown is, I have shown you two spheres and one cube. Now this sphere is made up of pure iron, and this one is a mixture of iron and aluminum, and this sphere is half made up of aluminum, and aluminum has got less density, that is 2.7 gram per centimeter cube, whereas iron's density is 7.8 gram per centimeter cube, and this is made up of pure iron. So the whole mass is concentrated at the geometric center. So this point is called center of gravity. Center of mass, center of gravity, one and the same thing. But here guys, the geometrical center should be generally the center of gravity or center of mass, but here the more massive portion, suppose this part is made up of iron and this part is made up of aluminum, so the more mass is concentrated over here, so the center of gravity would be towards more massive substance, so the center of gravity would be shifting over here, correct? So this point would be the center of gravity. Now this is again a pure iron cube, right? And wherever all the diagonals they bisect, that point is actually inside the cube. So this point is the center of gravity. That is the geometrical center of the cube. This point is inside. Now what happens is, the weight is a force that acts vertically downwards from the center of gravity. So weight of this ball would be shown like this. The weight of the entire cube can be shown vertically downwards like this. Again, the weight of the entire sphere can be shown vertically downwards. So if you want to show the weight, which is the force by which the earth is attracting these objects towards itself, then show it from vertically downwards from the point of center of gravity. Let's move on. Here I am going to show you the center of buoyancy point, right? So what am I going to do is, I am going to immerse a substance which looks like this, and this substance has got very light density, so it is not going to immerse inside the liquid. It is not going to sink inside, but you can see that still some part of that object is inside the water, or let's call this as water. Correct? So now this part of the object is basically inside the water, which means this much volume of substance. Suppose let's call this volume of substance which is inside as V1, and the entire volume of the substance, let's call this as V. So V is the entire volume, of body, whereas V1 is the volume of submerged part of the body. Now, which means the same volume of water would be displaced, right? So this part is very important for us, and its center, its geometrical center would be called as center of buoyancy. So what happens is, this part was initially occupied by the water, but when this part goes inside, this much amount of water or this much volume of water displaces up, and the volume and the center of the displaced water volume is the center of buoyancy. So this point, or in general you can also say that it is the geometrical center of the part of the body immersed inside the liquid. So somewhere over here, right? Whereas the center of gravity of the body is exactly at the center, the full center of the body. But here I am talking only about the center of the submerged part of the body, right? So if I want to show the weight has to be shown vertically downwards like this, but the buoyant force has to be shown vertically upwards from the point of center of buoyancy. So I have to point in the direction upwards the buoyant force from the center of buoyancy point, but the weight has to be pointed vertically downwards from the center of gravity, right? These points may match, these points may not match also, right? So here, this is case 1. In case 1, what am I basically talking over here? This is a liquid, right? This entire vessel is filled with liquid, and this is our main substance, right? And this substance, its center of gravity is exactly at the center, which is inside, where all the diagonals meet, and vertically downwards is the weight, right? So W is the weight of the body pointing vertically downwards from the center of gravity. Now here what happens is, I am already telling that the weight of the body is larger than the buoyant force. So that means the buoyant force in the upward direction, weight in the downward direction, downward force is more. So what's going to happen is, the body is going to sink. Correct? And this body settles down completely at the bottom of this tank, right, which contains, say for example, a liquid or a water, right? which means the length, breadth and height were L, B, H. So the volume of the body was L into B into H. Mass of the body is, say for example, L, and the density of this body would be rho body, and that is equal to mass of the body divided by volume of the body, that is L into B into H, right? Or it can be also simply written as M by V, right? So basically this was the section, right? This was the section which was initially occupied by the water, because the entire thing is water only. But now the moment I put this cuboid from the top, this cuboid is going to settle down, and it has now displaced the same amount of water, right, which is equal to its own volume. So the object's volume would be same as the volume of the liquid displaced. So earlier this part was occupied by water, now this part is occupied by this particular object. And so from this point, this is the center of gravity of this body. So I am going to write down W in the downward direction, vertically downward direction. But you may be amazed to know that this part was earlier occupied by water. Now the center of the submerged part of the body, that means again the same point, is called the center of buoyancy. So from the same point in the upward direction, buoyant force is going to work, right? But W is greater than B. So what's going to happen is W is equal to M times G, that is equal to buoyant force, which is equal to the density of water multiplied by volume of water displaced multiplied by G. Mass of the object can be written as density times volume. So density of the body multiplied by volume of the body multiplied by G is larger than rho W Vg. Vg getting cancelled from both sides, because the volume of water displaced is same as the volume of the object. And from here we derive a very important thing, that is density of the body. If it is greater than the density of water, then the body will sink. So an important thing to be remembered over here. And let's move on to case 2. In case 2, again the same object, but this time what am I going to do is I am going to make the weight of the body equal to the buoyant force, right? So here what is going to happen, this is the center of gravity. So the weight of this entire body is pointing downwards, that is W, which is equal to mg, correct? And this is again a case of sinking, right? And since the entire substance is submerged inside the water, but its top face is in alignment with the surface, so the full object is actually inside the water and its surface is matching with the surface of the water. So this is actually water, it is not an empty tank, right? So the volume of water displaced is again the same entire big volume, because earlier this entire volume was being occupied by water. Now the moment I put this cuboid inside, the same volume of water got displaced. So the center of the volume of water displaced, or the center of submerged part of the body, again is the same point, and this is the center of buoyancy, and vertically upwards would be the buoyant force, right? And I am making these two equal. So weight of the body, that is equal to mg, that is equal to rho of the water, v, that is the volume of the water displaced, that is equal to the volume of the body, times g, again rho body, v g, that is equal to rho water, v g, getting cancelled from both sides. So I can make an important point from here, density of the body, that is equal to density of water. If this is the case, then this cuboid can stay in equilibrium anywhere inside the liquid. So this may also be possible, that the entire cube is resting over here inside the liquid, because at any point the upward force, that is the buoyant force, is going to cancel the downward force, that is weight. So this cuboid can be placed anywhere inside the liquid in equilibrium. You can also apply force and put it over here, and then you can remove the force, but nothing is going to happen. This cuboid is going to stay over here too, because the buoyant force again and weight are same, balanced, right? So the peculiarity of this particular case is this particular cuboid can remain anywhere inside the liquid in equilibrium, right? But this is also called sinking, guys. So object sinks. Sinks in the case, since in the sink means that the entire body is submerged inside, its top surface is matching with the top surface of the liquid, correct? So let's discuss the last case, in which the weight of the body is less than the buoyant force, right? Okay, so weight of the body is less than the buoyant force, W less than B. So this is the object, this is the center of gravity, and the weight would be acting in the downward direction, and this is the submerged part of the body, this part, right? This part is actually inside the water, this is water in a container, and the center of the submerged part of the body, or center of the volume of water displaced, is the center of buoyancy, so buoyant force acting in the upward direction. Now let me call this buoyant force as B1, correct? Now under this situation, what is going to happen is, the weight of the body is equal to the buoyant force, right? Right now this W is equal to buoyant force B1, because the body is floating. Floating body means the net force acting on the body is 0. So net force means both of the forces have to be 0, and body is in equilibrium. I'm sorry, I made a mistake. So floating bodies are always stationary, net force acting on them is 0. Now what am I going to do is, I'm going to put my finger over here, and I'm going to apply some force F in the downward direction, and I'm going to completely submerge this block down. So that means the center of gravity would be downwards, the weight of the body acting in the downward direction, but the same amount of volume would be displaced. So this is the center of the submerged part of the body, so the center of buoyancy would be coinciding over here. Let me call this buoyant force as B2, and this weight is smaller than B2, because more you submerge the body inside, more part of the body goes inside, more volume increases, so the buoyant force also increases. Now this buoyant force is larger than our weight. So the moment you withdraw your force, which we were giving, when I remove my finger, this buoyant force is larger than the weight, so upward force is larger than the downward force, so the body is going to move in the upward direction, right? So when it is on the surface, this buoyant force value would be lesser than this buoyant force value, and when it is completely submerged, this buoyant force is larger than the weight, right? So we stick to this condition, and here weight of the body is equal to mass of the body multiplied by g, that is less than the buoyant force B2. Mass is equal to density of the body multiplied by the full volume of the body multiplied by g. Buoyant force is equal to density of liquid, volume of the submerged part of the liquid, and the volume of the submerged part of the liquid is again the volume of the complete body, because I am talking about this condition. right? So that is complete volume multiplied by G. You can see that both gets cancelled. So the density of liquid has to be larger than the density of the body in order to cause flotation. Correct? Let's move on. Very simple law of flotation. The entire weight of the body which acts downwards from the center of gravity has to be equal to the weight of the fluid displaced. You can call this as buoyant force, which is always acting from the center of buoyancy in the upward direction. Correct? So let's understand this. Now here I am showing a man who is floating on the surface of Dead Sea. Now Dead Sea has got lot of salt content, due to which the density of liquid becomes very high and the buoyant force acting in the upward direction becomes very large, which is equal to the weight of this man. And this, due to the high buoyant force, what happens is the weight is being perfectly balanced, so this man can even float without any kind of tires and anything else. So now when a body is floating, it is stationary. Stationary means net force is 0. So how many forces are acting on the body? 2. So that means weight and buoyant force has to be equal. Whereas buoyant force is equal to density of the liquid, volume of the submerged part of the body multiplied by the G, right? And if I attach a spring balance, say for example, if I attach a spring balance to this man, just joking, we can't do that, right? And spring balance, guys, always measures net force acting on the body. Spring balance measures weight also, which is acting in the downward direction. But which weight? Not this weight. Now the spring balance is going to measure the net force or net weight which is acting in the downward direction, which is 0, because the net force acting on the body is 0. So it would measure 0 newtons. So when a body is floating and when you try to measure its weight, there would be no net weight. So a body is said to be weightless when it is floating, right? Let's move on and understand the slide in depth about the law of flotation, right? So here I am having this part of the body which is underwater. This height I am calling it as h2. The complete height is h1. The area of the base, this base, is A, right? So the complete volume or full volume of the body is equal to area times h1. Now the volume of submerged part of body, that is equal to area of the base multiplied by height h2 multiplied by height, area multiplied by height h2. This is h2, right? And this would be same as the volume of water displaced. Now guys, this is the center of gravity and the weight of this entire block is downwards, and the center of buoyancy is the center of the volume of fluid displaced, or the center of the submerged part of the body. So buoyant force acting in the upward direction. Since this body is stationary, nor it is going down nor it is going up, so the entire weight of the body is equal to the buoyant force acting in the upward direction. Weight of the body is equal to mass into G. This is equal to rho of the water or the rho of the liquid multiplied by the volume of submerged part of the body, that is A times H2 multiplied by G. Mass of the body is equal to density of the body, volume of the body, G rho L A H2 G. This volume can be written as A times H1G, that is rho of liquid, A times H2G, GA getting cancelled. So the final answer, density of the body times H1 is equal to density of liquid times H2. Most important outcome of law of the flotation. The product of density of the body times the entire height of the body, that is equal to the density of the liquid times the height of the submerged part of the liquid. Right, a very important outcome, and I have highlighted the important points which were discussed till now in the last slide. So weight of the body, this is the characteristic of a floating body. Weight of the whole body is equal to the weight of fluid displaced. This is nothing but the buoyant force. We are familiar with the second point, right, that the weight of the body acts vertically downwards from the center of gravity, and buoyant force acts in the upward direction from the center of buoyancy. In floating body, as I told you, that we measure the weight of the body with spring balance. Spring balance measures the net weight on the body, which is 0. Very important point. So guys, hopefully you like my explanation. Stay tuned, because I am going to come up with the numericals now of the law of flotation and Archimedes principle. Thank you for watching the video, and do subscribe my channel.